Hello, in this video we're going to talk about the integrated rate law for first order reactions. Alright, so we're looking at the relationship between concentration and time. And so what we've talked about in previous videos is the differential rate law, and that tells us what the rate of reaction is as a function of concentration. So for example, your rate is equal to the change in A at some time, and then we've noticed that that's equal to a rate law constant times the concentration. But this gives you the rate, the slope of this line at some point in the curve. Well, you're taking calculus. You know that derivatives give you the change in things, and then before you take the derivative, you get the thing itself, right? So if we take this derivative and integrate it, we get what's called the integrated rate law. And this gives us the concentration as a function of time, which is just what this curve is itself, right? So integrated rate law gives you the curve. You differentiate it to the differential rate law, and it tells you how that's changing at each point. Remember, how it's changing is the rate. So integrated rate law tells us how the concentration changes as a function of time. You can imagine this is useful. We can figure out what the concentration is after some length of time or reaction. All right. So these equations that we do here, they depend on the overall reaction order. And so what we talk about in this video is overall first order. In the next video, it's overall second order. Well, what if you have something that's overall third order? What do? And the answer is you don't do this, right? You either deal with some trickier calculus, or what we often do in the Gen Chem setting is we just play experimental tricks. We will take the concentration of one of the reactants and set it to be really high, such that as the reaction proceeds, this concentration doesn't change at all effectively, right? It changes only a tiny amount. Then we have another reactant set at a really low concentration, and then we can deal with the changes in that one that's at the low concentration with all of this, and ignore the high concentration one. So that's called a pseudo first order reaction, and sometimes we do that too. But we do also just make a lot of vague statements about imagine a reaction where A goes to B, so we'll do that here. So again, let's think about this a little bit more. The instantaneous rate is the rate at a specific point in time. As you shrink down delta t, you get to an infinitesimally small chunk of time that we call dt. And, right, your instantaneous rate is the slope at this time. And we've described it like this. All right, kind of a recapping ground here. Now, in a overall first order reaction, we're just going to say A goes to B, whatever that is. Let's calculate the integrated rate law. Or let's do calculus, I should say. All right, y'all are taking calculus. Hey, look, we get to use it in chemistry finally. So at the start, here's the equation we're dealing with, change in A with time, and we switch the deltas into d's because we're talking calculus now. And all right, let's integrate this thing. So before we do that, we need to separate the variables and put the concentration of A on the left and then time on the right. And now we can integrate this from the initial point in the reaction to some time. So on the left, that's the initial concentration to the concentration at some time. And on the right, that's the initial time to some time. So you do this integral, and you get this result. So you have the natural log of A at some time minus the natural log of A. And then you have kt, negative kt. And this is because when you take the integral of 1 over x, you get the natural log of x. And then your natural log of x at time t minus your natural log of x at time 0. That's because you put in the boundary conditions after you did your integral. All right, so here's our result. We'll rearrange it a little bit, and we'll call this the integrated rate law for an overall first order reaction. And this is the one you get on your info sheet. Now, we can play with this a little bit, right? Here's this equation. Well, we can also bring it back to this form. Here's this equation here. We can rearrange it this way. And this is effectively y equals mx plus b, if you look at it. And we call this the linear form, right? Y is the natural log of A at some time. All right, that's what's changing. Great. T is our time, so that's our x-axis variable. And k is effectively the slope there. And then the natural log of the initial concentration of A, well, that doesn't change because that's your starting point, right? And that doesn't change as you go, so we can call that the intercept. And so if you plot this, so on the y-axis you have natural log of A as opposed to A, which we were talking about before, then you get a straight line with the slope equal negative k. And so this is one way that you can determine the order of a reaction overall, is if you plot the data this way and you get a straight line, great, it's first order. If you don't get a straight line, it's not first order. All right, we can also take this and take e to both sides, right? E to the natural log of x just gives you x. And so this will get rid of the natural logs for us and give us the exponential form, which is also nice, right? It's nice to have this way to phrase the equation if you like it. And then when you plot this, you just get the normal curve like we were talking about on the last couple slides, concentration of A and how it changes with time. Okay, so we have our equation now. And before we get into calculations, we need to talk about Sig Fig rules. Because, well, we haven't done sig figs on logarithms yet. Or maybe you did in your Chem 8, but you may not have as well. And so these have different sig fig rules, and we need to go into it here because now we're doing logarithms with experimental data. So when you take a logarithm, there's a difference between the number 3 here and then the exponent 10 to the 4th. All right? So this 10 to the 4th comes out, and it's generally the number in the front of this decimal place. And then this experimental data after the logarithm turns into this number after the decimal place. And so we have names for these, right? The number in front is the characteristic, that's this. The number in the back is the mantissa, that's that. And so the mantissa, the stuff after the decimal point, has the same number of sig figs as your original number. That seems kind of like cheating. In effect, you gain a sig fig, but that's what happens, because the first number is not really a sig fig, it's an exact number that tells you that it was 10 to the 4th. Another way of looking at this is if you have log of 3 times 10 to the 4th, well, logarithm rules, if you have log of a times b, that's equal to the log of a plus the log of b. So we can split this out. Log of 3.00, log of 10 to the 4th, right? Log of 10 to the 4th just gives you 4. The log of 3 gives you this number. And then you can add these together, and now the first one's exact, so it doesn't really count for your sig figs, and the second one has those 4 sig figs from that experimental number. All right, so that's logarithm sig fig rules. Another example, this works for natural log as well. If you have the natural log of 4 times 10 to the 4th, plug it in your calculator, you'll get 10.5966. Now, since there's only one sig fig right here, that means there's only one significant decimal place in your logarithm. The 10 comes from the fact that you're taking the natural log of 10 to the 4th, so this part here is exact. Now, going forward in your calculations, this thing will in effect have 3 sig figs. So it seems like you gained a couple sig figs, and you did, in effect. Alright, now we also need to talk about the AntiLogarithm Sig Fig Rules, and it's basically the reverse of what we just talked about. So you take your number that you're taking 10 to the whatever of, and split it at the decimal point. So on one side you have the characteristic, the other side you have the mantissa. In effect, this stuff here is your experimental data, and so then you have 3 sig figs in your answer. So you can phrase it this way, right? The resulting number has the same sig figs as the mantissa in your logarithm that you're undoing with your anti-log. And then maybe this is best shown with another example. So e to the negative 12.2, again this works with e as well, as 10 to the whatever. And so e to the negative 12.2, well negative 12 gives you this information that it's 10 to the negative 6, right? So the 12 goes to that. And then your experimental data, which is this right here, it comes in and lands right there. So you'll have the number of sig figs total that you have decimal places in the number that you put up in the exponent there. Just the reverse of the logarithm sig fig rules, so at least it's consistent that way. Alright, so now that we know that, let's deal with an example. So you have your reaction, say you go from A to B, and it's first order in A. Now you're given a rate constant, and you want to know how long will it take for the concentration of A to decrease from some starting value to a final value. And so here's the equation that'll be on your info sheet, and you're told it's first order, so you use the first order version. Here's our initial concentration, here's where we're trying to get to. And so we can really just plug these numbers in and solve for t, right? So you can rearrange it for t, and then plug numbers in. Okay, right, you get your rate constant from the problem. And then now thinking about logarithm sig fig rules, right? If you take the log of this stuff, that's the same as taking the log of 0.159, Right, so you do this division, you get 0.159. Since you have 2 sig figs in each of these, you'll get 2 sig figs here. And now, when you do the logarithm, well, the 0 is your order of magnitude, and so that becomes this -1 up here, and so it doesn't count for your sig figs. And then the 0.15, well, there's 2 sig figs here, so then you have 2 decimal places in your resulting number after the natural log. All right, so now in effect, you have 3 sig figs divided by 2 sig figs. Your overall answer is going to be 66 seconds with 2 sig figs. So again, double check the units here. You can do the rate law constant in inverse seconds, inverse minutes, inverse hours, whatever. So then just play the dimensional analysis game. As you are dividing by inverse seconds, you just get seconds out. And so that's how to use the first order rate law, the integrated version. So thanks for watching, and in subsequent videos we'll talk about the second order version of this as well.